Hello, and welcome to Homework 4, Part 1 here, where I'll be deriving the heat diffusion equation for Cartesian coordinates. And so, let's hop right into it. And this figure will be a three-dimensional cube. And so, I'll draw it right here. All right, so let's define our coordinate system. All right, so this figure had heat flow going in the x direction, heat flow going out in the x direction after some differential distance in that direction. So this will be dx, this will be dy, and this will be dz. So they had that drawn for every single face, and so this was heat flow in the z direction, this was the heat flow going out after some differential z distance, and then same thing for the y, heat flow going in, and heat flow going out after some differential y. Then in the cube was this e dot g and this e dot st. And I'll get those two later here. And so let's talk about how they defined this heat flow after some differential distance. So it is actually defined in the book as, so I'll do the x here. So the heat flow after some differential distance in some certain direction, in this case x, is the heat flow initially at the other face plus the rate of change of the heat flow in that direction with respect to that direction, in this case x, and then times the distance they traveled. So that sort of makes sense. You know, it's kind of like slope intercept in an odd way, so to speak. And so this is the same for y and z. So I'll just quickly write those. Well, not so quickly. All right. And so let's move on to those two terms that I had put off earlier. So what is this E dot G? It is the rate of energy generated within this differential volume. And so what is it defined as? It is defined as the rate of heat generated per unit volume. And so to get it in terms of the differential volume, we multiply it by the differential volume. And so then moving on, we have this E dot st, which is the rate of energy storage or the rate of energy stored. And that is defined as rho Cp. And so that is sort of the Q dot in this situation, which this is sort of the amount of energy that is storable per unit volume. And sort of to double check that with the units, this is kilogram per meter cubed. This is joules per kilogram Kelvin. Kilograms cancel out, so you get joules per meter cubed, so energy per unit volume, Kelvin. And so to get that in terms of the differential volume, that is also times by dx dy dz. And there's this added term where the rate of the change in temperature depends on time. And so this ultimately gets it to watts. This is in watts. And then all these other heat flows are in watts. And so how do we get to the heat diffusion equation, right? Well, we just do an energy balance for this differential volume. And so it has to be the rate of energy going in plus the rate of energy generated plus, oh, not plus, minus the rate of energy going out is equal to the rate of energy being stored. And so everything is in watts, so that's rate of energy. So we just plug in everything that we've defined. So rate of energy going in. So it's going to be all these heat flows with an arrow pointing into the differential volume. So it's Qx plus Qy plus Qz. I will skip the energy generation for now because there's a cancellation that is more apparent if you put them side by side. So minus the Qx plus, so these terms now, since they're all pointing out, and I never write, I always end up writing more too big, so I can never fit the heat generation. So Q dot dx dy dz is equal to rho Cp dx dy dz t time. All right. So this negative gets distributed to every term in here, and you can notice that then this becomes negative. The heat flows all become negative, so they cancel out with the positive heat flows. And we're just left with the negative, this sort of change here. So let's write that out. Dx minus Qy dy Qz z dz plus Q dot dx dy dz is equal to rho Cp dx dy dz. Change in temperature, that depends on time. All right, so let me make sure my phone cam is still going. All right, good. All right, so where do we go from here? Well, there is another way that we can express these heat flows that we haven't done yet, and that is with Fourier's law. Fourier's law. And so let's do that to see if it gets us anywhere, and it will, which is why I'm doing it. So let me move my paper up a bit here. Fourier's law is the heat flow in some direction. I'll do x, and that is equal to the heat flux, or the rate of heat flow per an area. So since this isn't per an area basis anymore, that means this per area was multiplied by an area. Makes sense. So the heat flux times the area, which the heat flux, like I said earlier, was the heat flow through an area, or per an area, same thing. And so what is the heat flux? Well, this is the Fourier's law part, which is the negative K, which K is the thermal conductivity. And then that is times the temperature gradient, which is the change in temperature with respect to position. And the area that this heat flow X is going through is this differential Y and differential Z. And we do this for all of the directions. So it'll take a bit to write here. All right. So we actually stick in these heat flows for with respect to whatever direction they are at into these partial derivatives here. All right. And so when we do that, these negatives cancel. And so I'll write that. So this I'll just write out here. So k d dx dx dy dz. So dx dy dz. Plus this. Dx dy dz. And then dx dy dz. Dx dy dz. Plus q dot dx dy dz is equal to rho cp dx dy dz. And then this temperature dependence on time. And so next thing we do here is divide out that dx dy dz. And so another thing that I'll do here in the same step is that, well, let's make the assumption, and this ties in with the linear approximation that we were able to do up here. But what ends up being a linear approximation up here is the fact that we're going to say that K is independent or does not depend on temperature, and then therefore then it ultimately also does not depend on position. And so we can say K is constant and pull it out of this differential, which if it did depend on it, it would have to stay in there. And so I'll be pulling a K out. All right, so it'll be like sort of like K times this whole parentheses unit here, this entire term, not these ones, but this term up here. And so I'll also divide it out. I'll also divide each term by then K. So I'll do divide by K after pulling it out, and then I'll also divide by dx dy dz. So that's what I'm doing in this one step here. So we get, so these two combine to turn into a double derivative, or double partial derivative, I guess, since this is multi-directional. Yeah, derivative to the second power. So dx squared plus, then in the y direction, and then in the z direction, then q dot over k is equal to rho cp over k, and then that temperature dependence on time. All right, and so this might seem like it's it. We're actually almost there. It's just that we can make one more simplification, that rho cp over k. And so that is actually the inverse of the absorptivity of whatever material that we're using for this differential volume, I guess. No, I guess, yeah. And so let's simplify that down. Which makes sense that it would relate, absorptivity would ultimately relate to the storage, right? And so this will be our heat diffusion equation for Cartesian coordinates, right here. Let's go. Yay. All right. So, see you in part 2.